My name is Anne Lullier. I am from LUND University, and this presentation is an introduction to high-order harmonic generation in gases. In the first part, I will briefly introduce the subject. Then I will talk about the dipole phase, and finally I will discuss properties of attosecond pulses or harmonic pulses. High-order harmonic generation was discovered at the end of the 80s when studied the interaction between atoms and a strong laser pulse. The experiment consisted in focusing a laser into a gas cell and then looking at the radiation with a grating and a photon detector. The aim of the experiment was to study the fluorescence from these gases, but instead we observed the generation of high-order harmonics of the laser field. Here you have one of the first spectra obtained in argon and showing harmonics from orders 13 to orders 31, only odd-order harmonics. What was very interesting is that when plotting the intensities of these harmonics as a function of process order, we saw a characteristic behavior with a first decrease, then a plateau behavior, and finally a cutoff. And I think that the most important discovery was this plateau behavior. At that time, we were thinking very much in terms of perturbation theory, where you expand the polarization induced by the laser in series of powers of the electric field. And for such an expansion to be valid, you assume that the first order is much larger than the third, much larger than the fifth, etc. And this was obviously not the case. Strong, nonlinear, non-perturbative effect. This process is in between two physics topics. One is quantum physics, which describes the single atom response, and which is described by the Schrödinger equation, which you can see on this slide. With on the second term, you have the atomic potential and the laser-atom interaction. You can write this laser-atom interaction using a classical field and using the dipole approximation. But it is also important to consider the response of all of the atoms in the interaction medium. This is part of electromagnetism, is described by Maxwell equations or a wave equation, such as the wave equation that you see here, where you have a generated field due to a polarization in the medium. And it is important to have a certain phase matching condition in order to have high-order harmonic generation when the waves from the different medium from the different atoms in the medium add in phase. There was a huge progress in understanding high-order harmonic generation in '93 due to a very nice intuitive model proposed by Paul Corkum and by Ken Kullander and co-workers, and which is presented on this slide. First, what you see is the atomic potential, which is strongly deformed by the laser field, so that an electron in the ground state can tunnel through the potential barrier. Then the electron is driven away by the laser field, and when the laser field changes sign, the electron can come back towards the atom with a high kinetic energy and recombine back to the ground state. And in this process, you have the emission of a short light pulse. This model, so here I have some acronyms, time-dependent Schrödinger equation that was used to simulate this process in the first place, the three-step model, which I have just described, and finally the strong field approximation, which was proposed by Maciek Levenstein in '94 and which has been used a lot in this field. Going back to harmonic generation, using this model, we have understood the process in the time domain, and this process is actually repeated every half laser cycle, first on one side of the atom and then on the other side, leading to the emission of a series of short attosecond light pulses, which are separated by half the laser period and with a sign flip between consecutive pulses. And now if we go from the time domain to the frequency domain, you recover the spectrum of high-order harmonics. So this concludes this very brief introduction. Now I'm going to go in more detail into the physics of high-order harmonic generation, and first the single atom response. So let me come back to the three-step model as shown here. And now what is very nice with this model is you can do simple calculations, which I really encourage you to do just to learn the physics. So let's calculate the trajectories of the electron when they are emitted from the atom. And this is the Newton equation describing the acceleration of the electron due to the laser field. Now you can integrate this equation. You need some initial conditions, which are very simple. We assume that the electron is born at a certain time, Ti, at position 0, close to the atom, and with a velocity equal to 0. And you can then integrate this equation and then a second time to obtain the trajectories of the electron, which are shown on this slide. And here you see that you have an ensemble of possible trajectories depending on the ionization time, with indicated in different colors here. First, there are trajectories in dash, which are the trajectories not returning back to the atom. The atom is then simply ionized. And then you have trajectories which are either long, these are in red, or short in blue, which means that the trajectories takes more or less time. What is important is actually the velocity that the electrons has when it returns. So the next step in this calculation is going to calculate the time of return of the trajectories and also the velocity of return of the trajectories. Therefore, we can now calculate the kinetic energies of the electron when they return. And we can then plot this kinetic energy as a function of the return time. And you find that this kinetic energy varies from 0 to a maximum and then back to 0. And the blue part is the short trajectory and the red part, the long trajectories. And you see there is a maximum. This maximum leads to a maximum in kinetic energy, you see, and it's equal to 3.17 UP, where UP is defined here, is the ponderomotive energy. Now we can go from the kinetic energy of the electrons to the frequency of the XUV radiation which is emitted simply by adding the potential energy of the atom. And here what is represented is the photon energy as a function of return time, starting from IP to a maximum photon energy, which is given by IP plus 3.17 UP. So this very simple model, which you can calculate yourself, just solving Newton equations, allows us to understand an important characteristic of this high-order harmonic generation spectrum, the presence of a sharp cutoff with this kinetic energy. This curve showing the frequency of the radiation as a function of time can be parameterized. You can see that this curve here for the short trajectory can be approximated by a straight line, and similarly for the long trajectory. So what we do is we go from the variation of the frequency as a function of time using this linear approximation. From the delay, we inverse this variation to obtain the delay as a function of frequency, and from the delay we can perform an integration, and we get the phase as a function of frequency, the spectral phase, which is also called the dipole phase. And this can be done for the short trajectory and for the long trajectory. And using this mathematics, which I don't describe here, we can get a very nice expression for this dipole phase, which is shown here, which depends on the frequency and on the laser intensity. And what you have, this is very similar to the development of the spectral phase of an ultra-short pulse, which is usually expressed as a function of the carrier frequency. Here, it's not the carrier frequency, it's the threshold frequency, omega p. But it's a similar development with three terms: a phase, delay, and a group delay dispersion. And what is very nice is that the first term and the last term depends on the laser intensity. The group delay does not depend on the laser intensity. And this expression is very useful to discuss the properties of this radiation. We can calculate the coefficients of this expansion very easily, and here they are expressed as a function of different constants and parameters. Actually, the only parameter which is needed is the wavelength of the laser. The rest are constants: the speed of light, the fine structure constant, and the mass of the electron. So these are the expressions for these coefficients which are important in this parametrization of the dipole phase. This brings me to the last part of this first part of the introduction: properties of attosecond light pulse or harmonic pulses. And let me start by attosecond light pulses and the temporal properties of the attosecond light pulse. Looking at this expression, you see that you have a term which is the group delay dispersion. And let's look at the coefficient of omega minus omega p square. You have a different variation depending on whether it's a short trajectory or a long trajectory. In the case of a short trajectory, gamma s is positive. This means that the GDD of the attosecond pulses is positive. There is a positive chirp. So you should stop thinking of attosecond pulse as a simple transform limited pulse. As shown here, it's a strongly chirp pulse, as shown here in this example. For the long trajectory, the gamma coefficient is negative, so this is a negative group delay dispersion, and the attosecond pulse will look something like this. Let's now look at the temporal properties of the harmonic pulses. And now here I am expressing the chirp coefficient B, which is the second derivative of the phase with a minus sign. So you can write this second derivative as a derivative with function of the intensity times the double derivative of the intensity. This is for t close to 0, close to the centrum of the pulse. Using a Gaussian approximation for the pulse, you have an expression for the double derivative of the intensity, it's negative sign, and that means that B is simply proportional to this derivative of the dipole phase with respect for intensity. And this is a plot of this derivative with function of the intensity. There are two colors here which refer to this very simple parameterization that I have presented, as well as a calculation using the strong field approximation. You see that both calculations agree very well. And what you see on this plot is that this derivative is always negative, so the harmonic pulses have a negative chirp, close to 0 for the low order harmonics generated with a short trajectory, and it decreases. And then for the harmonics generated with the long trajectory, it's also negative, and this time getting more and more negative for the low order processes. Let me now discuss the spatial property of harmonic pulses, and let me start by a little bit of Gaussian optics. Here what you have is the expression of a Gaussian field with, I want to especially look at the phase property of these Gaussian beams with a quadratic phase as well as the GUI phase. So now let's look at the harmonic generation from this Gaussian pulse. then the phase of the harmonic field will be equal to Q times this phase of the Gaussian beam plus this dipole phase for a certain trajectory and as a function of intensity. And now we are going to look at how this dipole phase depends on the intensity, the spatial parameters of the intensity. So now let's look in more detail at the influence of these two terms. First, the transfer of the phase of the laser and leading to the wavefront, which is indicated here in black. And this wavefront is varying from negative to positive. Now let's focus on the case of the short trajectory using the parametrization that I have presented already. And now we find that a simple quadratic dependence with a gamma s, which is positive. So the dipole phase will lead to a wavefront, which is indicated in green, which has always the same radius of curvature, and which is positive. So if you now sum these two phase contribution, you will see that you have to consider both terms, and there will be a position which is before the focus, where both radius of curvature will compensate each other, and where the harmonic field are going to be generated in a flat wavefront. And depending on where you are, the wavefront can be positive or negative. So if you now are here before this blue line, the harmonic will be generated in a conversion beam with a focus, which will be on the right. It's a real focus. On the other hand, if the generating beam is on the other side of this flat wavefront curve, then the focus of the harmonic will be before, it will be a virtual focus. So very, very different spatial properties depending on the position of the generation medium and because of the influence of this dipole phase. So this depends very much on the order of the process. It depends very much on the photon energy. And here you have an example where the generation medium is here before the focus. And depending on the process order, you will have virtual foci or real foci. Real foci for the low frequency and virtual foci for the high frequency. So when you refocus the radiation, you will get a very extended XUV photon. And this is obviously a difficulty if you want to have very short attosecond pulses. The attosecond pulse will exhibit spatial-temporal coupling. The electric field cannot be written as a product of the spatial part and the temporal part. They are coupled. And this obviously leads to a problem how to focus the attosecond pulse and keep the very short pulse duration.